So today, we're going to be making moonshine together. Now, I know. Moonshine is nothing on the front screen, but we're going to be fancy. We're going to be special, and we're going to call it ethanol instead of moonshine. But folks, it really means the same thing. And instead of going back up in the woods and using a still, we're going to be using fancy, expensive pieces of glassware in order to make our moonshine, and we feel better about ourselves because we're in a lab space making it. Well, this is legal. Don't take anything out of context because you're going to end up with a very small amount, and I hope that you're not going to try to sell that, and if you do, please do not let me know about it. So today, we're going to go on a journey, and we're going to talk about the fermentation of ethanol and the distillation of ethanol, which basically, in layman's terms, is moonshine production. So how do we do it? Well, if you follow the lab procedure is first going to tell you to start off with some sugar. This sugar is going to be the foodstuff that our little bitty yeast creatures will begin to eat. So on the balance, here you see a weigh pan, and I've tared the balance out, and you're seeing 0.0000 grams that is prepped for me to be used. All right, so then I go to the laboratory and I get our sugar. You know, I could be fancier and I could order special lab grade sucrose and have it sent to me and we can use that. Or we could just simply use good old fashioned granulated sugar that you would find in the grocery store. So that's what we decide to use in this experiment. We don't need anything super fancy, super expensive, super chemical pure. So granulated sugar is perfectly okay here. As far as the label goes, this again is one of those times that you would write in stock because you don't know where that sugar came from. You don't know the brand. You don't know the lot number. You don't know anything. It's just a stock container that our laboratory has provided you. If you want to know the sugar observations, here's a close-up picture of the sugar. It looks like any old sugar wood that you would use in your kitchen or at home. So there's nothing special about this sugar. And once again, you can make the observations as you see fit. So I poured the sugar into a weigh pan, and on the weigh pan and on the balance, you're seeing the mass of the sucrose. So this is the mass of the sucrose only. This is not including the weigh pan because I have tared the weigh pan out. So 37.1504 is the mass of the sugar that we've decided to use in our fermentation process. All right. So I think the lab says 35, and this is close enough. Whatever. I mean, we're in the ballpark vicinity. We're going to get ethanol. We're going to get ethanol. So no big deal here that I'm 2 grams over. As far as the yeast goes, that's our next component of the ethanol production. The yeast are the little bitty creatures that are inside of that flask that begin to eat the sugar and began to burp out, pee out, poop out, whatever you want to call it, our ethanol that we like to maybe drink on the very end process of this. All right, so here's the label information for the yeast that we've decided to use this go around. And this yeast label does not include a lot number. So as far as I'm concerned, what you see on the screen right now is a good enough label information for our yeast that we have to use in our lab experiment. So once again, I go back to the balance. I tear it out. I've got a new weigh boat that's on the balance pan, and then I add my yeast, and the lab procedure tells me about 3.5 grams, right? So I go and I try to get as close to 3.5 as I can, and sure enough, I did a pretty good job the first time around. So 3.5036 is going to be the mass of the yeast that we have used in this experiment. Now, I've not mixed anything together yet. I'm just weighing things out. That's all I'm doing. So this is like me in the kitchen getting a recipe together, making sure I have all of the ingredients that I need in order to make my cake. And that's what I'm doing here with all of these reagents that we have to have for fermenting our alcohol. All right, so the next kind of recipe is going to be our pasteur salt. And the pasteur salt's recipe is actually on the left-hand side of one of your laboratory experiment pages. So when it talks about the procedure, in that procedure or background information, the pasteur salt recipe will be located on the left-hand side of that page. You'll see it, just look for it, and it will give you the names and it will give you the amounts of each one of those compounds that we need. So the very first that we're going to start with is actually called potassium. I don't know if you can see this or not, but it says potassium dihydrogen phosphate. So this is one of those names. It might be called something different in your lab experiment. If so, then that's okay. It goes by different names. It has different terms that we can use, especially for the dihydrogen component of this compound. But that's the component that we're going to start with first. So this is the bottle. This is what it looks like. Strim Chemical is going to be the manufacturer of that chemical. And then over on the other side of the label that you see on the right-hand side of the screen, you're going to see your lot number, and the lot number is right there. So the lot number looks like it's A3756107. All right, so I'm going to take this potassium compound, this potassium dihydrogen phosphate, and I'm going to make some pasteur salts with it. So if I open up the lid, this is what that component looks like. It is a traditional white powder. Folks, it seems like everything, more or less, is going to be some type of white crystalline or white powder for us, and this is no exception. So that's what the potassium compound looks like. Again, I tared my balance, and the recipe tells me how much to weigh out. So I weigh out 2.1000 grams for my potassium compound. All right, so it's not perfect, it's not exact, but no one said it had to be, right? We're not really playing analytical here. The only thing we want is to make some ethanol. As long as these components are in there in the ballpark figures, that's really all that matters. All right, so the next component of the pasteur salts is the calcium phosphate monobasic. And again, that comes from Strim. And over on the other side of the label, you're going to see the lot number. And this lot number is A0846067. So if you had to guess, what do you think this calcium compound is going to look like? Yeah, ding, ding, ding. It's a white powder. And there you go. So this one's pretty full. I mean, you can see it all the way up to the rim. This one's a little bit chunkier just because it's a newer, fresher bottle. And as soon as I took a stirring rod to it, it broke up pretty well and it turned into a powder without a problem. So the mass of the calcium compound that I decided to use was 0.2360. Again, it's not a perfect match in the lab manual, but that's okay. I'm at least close enough. The next component of the pasteur salts, yes, this is the third component, is magnesium sulfate. All right, so magnesium sulfate is going to be a powder. If you look at the manufacturer here, it's the Mallinckrodt Chemical Association, or provider or supplier, however you want to call them. And it looks like I need something to do with lot number. Well, the lot number is right here on the very front of the label. Up here at the bottom, or up here at the top, you're going to see actual analysis, and it says lot, and it's G24160. So once again, if you had a guess, what do you think it's going to look like? And if you said, surprisingly, a white powder, then you're good. So this is another white powder that we use in a laboratory. I know it's kind of boring, but so far, 3 and 3, they're all been white powders. Well, my sugar has been a white powder as well, so there's 4 and 4. Now, the problem here is that I forgot to take a picture. I know, I was a little slacky this time, and I forgot to take a picture of the magnesium compound weight before I went on to the next one. So I went ahead and wrote it down for you. I forgot to take a picture, so the written value that I had in the laboratory during that time was 0.2268. So again, I am not perfect. That's not what the recipe called for, but I am close enough in order for this recipe to work. Finally, our fourth component, our fourth and last component, is something called ammonium tartrate. All right, so ammonium tartrate is going to come to me from MP. That is the company that produces this compound. So MP Chemical, or just simply MP, is very acceptable. And the lot number for them on this compound was 2940J. You're seeing that up here at the very top, and once again, it might be a little hard to see. So if you had to take a stab, what do you think this is going to look like? Surprise! Yeah, it's a white crystalline substance this time around, just like in all the other times. Well, there's a few differences. This one's more rocky, it looks more sugary, it's more crystalline, and some of the others were more of a powder. So that is an observation difference between the two if you want to start writing those down, but they all really are in the same, what I would call, category as far as observation go. They're all white, they're all somewhat crystalline or powdery, vice versa, and so forth. All right, so the mass of the ammonium compound is going to be here, and this is 10.1204 grams. So once more, not perfect, I don't have to be, but I've at least have my 4 components that I need in order to make my Pasteur salts. The Pasteur salts are really going to be a, I would say, dessert for the yeast. It just helps nourish them, so that way if the sugar begins to not satisfy the yeast demands, then the Pasteur salts are going to kind of help things out. That's one of the reasons that we use it. There's actually a couple, but that's one of the reasons that we begin to use it. All right. Okay, so here what you're seeing in the picture, I need to make, this recipe is going to make 1,000 milliliters of Pasteur salts. So this is going to be the total volume that I have. I know that I don't need 1,000 mils, right? So the issue here is waste. You know, I'm getting ready to be wasteful. But typically what happens in our lab is that multiple people will be fermenting at the same time, and I'll get one person to make the Pasteur salts, and it will be enough for everybody to use, and we'll have some left over at the same time. The issue here, though, is that it was just me. I was the only one that was fermenting the alcohol. I was the only one that needed the Pasteur salts. So why did I make so much? And the problem here is because some of the amounts that were used for those chemicals, they were really, really tiny. Okay, they were 0.2-ish as far as grams go. And if I scaled this down, then that means I would have to scale down those amounts as well. And I just really wasn't comfortable with that. I didn't want to go too low where I was just measuring out a couple of specks of a compound, thinking that that was going to be good enough in order to go forward with. So this is one of those times where wasteful is okay. And the reason I'm saying that is because these were, again, really tiny amounts. I didn't have to weigh out a lot of these compounds. And this is mainly water. So I'm getting ready to fill this volumetric flask up with water. That's the majority of the component, and that's perfectly okay. I mean, I know that we're going to have to dump all of this down that we don't use, but whatever. 0.2 grams here, 0.2 grams there, and then the majority of it water. I'm okay with that, and you should be okay with that as well. All right. So what you're seeing in the picture right now is a volumetric flask. All right, so a volumetric flask, if you've taken classes with us before, you would know what that is called. If not, now you know. So there's a volumetric flask. Up here at the very top, you probably can't see it that well, but there is a very faint line, and you can see where my cursor is at. So normally what happens here is that I'm going to take all of these salts, and they're all included in that one-way boat right there, and I'm going to dump all of those salts into the volumetric flask, and they'll sit down here below, of course. And then I'm going to add some water into the volumetric flask. I'm going to give it a good swirl. I'm going to make sure that everything gets dissolved up. And then once everything gets dissolved, I'll take this volume all the way up until that very faint etched line that is right there. So the bottom of the meniscus has to sit on that faint line. Now, why did I use a volumetric flask? I didn't have to, all right, but it was very convenient for me. Again, I'm not making analytical work. I'm not making sure that all of these things are super, super close to what they need to be. I don't really need full concentrations of things. I just need ballpark figures one more time. So I could have easily chose a beaker that was 1,000 milliliter beaker and dumped all of these compounds in it and added some water to it and stirred it up and called it a day. But the volumetric flask was nearby. It was the closest to me. It was suitable, and that's just what I decided to use. All right, so here you're seeing a picture of me dumping all of those Pasteur salts into the volumetric flask. It all went in at one time. Once more, just like normal, kind of routine here, you're starting to learn that, is I'm rinsing out the whey boat as I go. So what did I rinse it out with? Well, I rinsed it out with water, and that's because that's the solvent that will also eventually go into my volumetric flask as well. So that just makes sure that I rinse everything out of the whey boat when I begin to transfer these compounds over. And again, what you're seeing on the screen, a volumetric flask was not required. I could have used an Erlenmeyer flask. I could have used a beaker. I could have used a graduated cylinder. It really did not matter. I was just shooting for 1,000 milliliters, give or take, and that was about it. All right, so I added some water, and here's some observations if you want to take those down. So some water goes into the volumetric flask, and I just kind of let it sit and hang out. I begin to swirl it. You can see that it's cloudy. You can also see probably that it's not dissolved everything fully at this point, and that's because I do need to add more water, but these are the starts of our observations as we go forward. All right, so I added some more solvent, which is water. And once again, I give the volumetric flask a couple of shakes, 3 or 4 shakes, turn it upside down, roll it around, do whatever you need to do with it. Make sure that it's mixed fully and completely. But notice there's still a little bit of cloudiness that is left behind. So I'm not done with this yet because, as you can, of course, completely see, I'm not taking it all the way to the line yet in the neck of the volumetric flask. So there's still more work to be done, but this gets everything in solution and it gets those things beginning to dissolve. So I'm going to just kind of turn my back on it a little bit. I'll go and do something else, and I'll come back to these pasture salts when I'm ready for those. All right. So in the procedure, it also talks about this test tube, and it says that I'm going to have to make a test tube, and you need a saturated solution of calcium hydroxide. All right. So Ca, of course, stands for calcium, and I need a saturated solution. That's the key word there. Well, saturated solutions are very easy to make. What do? Well, you don't even look up textbook information, folks. I just simply take a scoop or 2 scoops of the compound, I dump it into a beaker, I add some water or solvent, whatever we decide to use, and then I just give it a good stir. That's all that I do. That's it. And if everything dissolves, I add more. If it doesn't dissolve, then that's good, because that means it's saturated. All right. So here's the calcium hydroxide that I used for the lab. Flynn Scientific is the manufacturer for this particular type of compound. And if you look at the lot number over here to the side, on the right-hand side, you're going to see lot number 118093. So that is the lot number of the calcium hydroxide that I have used in the laboratory to make this solution with. So once again, if I said, hey, what do you think the observations of this compound is going to be? And you tell me, white powder. Well, guess what? Yeah, you're correct. So go gamble on it, because you're right. So there is the calcium hydroxide powder. This kind of looks to me like baking soda or baking powder in a way at home. That's the texture. That's kind of the observation that I would make. Again, very white, very somewhat fluffy. It sticks together. And it's pretty dense, meaning that when I open the lid up, a lot of it's not going to go into the air. It's really going to kind of stay together, and it's going to settle when it can, unless I just really disturb it. All right, so I take a couple of scoops. I counted 7, I think, in total. And I just add it to a beaker. So again, the directions tell me make a saturated solution, and this is how I do it. So a couple of scoops into a beaker, I did 7 in total, and then I just dumped some water in it. I really didn't even measure anything, but by the looks of the beaker, here's 50, there's 100. It looks like I'm at the 100 mil mark pretty much. I mean, that's kind of where that level is going to be, or maybe a little bit above. As you can tell, 150 is above that. So I just added water. I gave it a good stir. And then again, I walked away from that because I need that to settle. And the reason is I need to make sure that it is saturated. And if it's saturated, then what I should see is a solid that begins to form down here on the bottom, and I should see more of a clearer solution up on top. Now, it might not be completely clear, but it's clearer than what it is right now. I mean, the way that this looks now, it looks like milk, right? I mean, it looks like a beaker full of milk, and you're getting ready to put some cereal or something in it, or an Oreo cookie. All right, so there's the calcium hydroxide saturated solution. When I turned around and went back to this solution a little bit later, then this is what it turned out to look like. And again, you see that that top layer, which is that solution layer up here on the top, it is getting much clearer, and I do see a lot of solid that's down here at the very bottom. So did it all dissolve? And the question is no. And that's actually a good thing, because I'm making a saturated solution. And if all of that solid dissolved, then it would not be saturated, and I would have to add more calcium hydroxide until I see that precipitate or that solid settling on the bottom. All right, so now I need to go and look at my fermentation setup. So this is what the book tells me to do, and here are the pieces and parts for the fermentation aspect of the lab. So what I have is an E flask, and E, of course, stands for Erlenmeyer flask, but there is an E flask, and it's a 500 ml Erlenmeyer flask. So that 500 ml Erlenmeyer flask is going to get my solutions. It's going to get my sugar. It's going to get my yeast. It's going to get my water. So this is where the fermentation is going to take place. Well, when that yeast begins to eat the sugar, then I told you that that yeast begins to burp and pee and poop out all of that wonderful alcohol that we like to distill off and capture and bottle and drink and sell. All right. So what happens is that that yeast will also release some carbon dioxide, and that carbon dioxide will begin to escape, and it will go up through this tube, and the cork's there just to force it up the tube, and over it goes, and CO2 is still traveling, and then it will eventually reach the test tube over here to the right-hand side, and bloop, 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 there goes the CO2. Now, the reason that we keep an eye on the CO2 is that we look for bubbles. All right, so the bubbles are going to be the carbon dioxide that the yeast is producing. So as long as we see bubbles, then that means that the yeast is still working. And that yeast, as long as it's working, is still producing alcohol. When I do not see any bubbles show up any longer, then that means my yeast is pretty much dead at this point. It's not producing alcohol anymore. So that's a very good sign to take away this fermentation apparatus and begin to distill off my ethanol. Now, sometimes it can be a trick, so I don't really want you to pay attention to bubbles too big of a deal, right? I want you to pay attention to them. I want you to see them. I want you to maybe record them on what you see and how long they stay. But at the same time, this is not the ideal scenario where it happens every single time the same way. Yeast are funny little things, and sometimes they produce enough CO2 that we can visually see it, and sometimes they're producing it in low amounts, and we might not actually see those bubbles with our own eyes, but they're producing and they're making alcohol. So for that reason, we tell you just walk away and come back in a few days. That's why we do that. All right. So over here on this test tube side, in order for me to see these bubbles, I'm going to have some kind of liquid. I mean, imagine you blowing through a straw. And if you blew through a straw in a cup that had liquid, you're going to see some bubbles that rise up to the top, right? That's your CO2 that you're blowing out. Well, the yeast has CO2 that they're blowing out as well. So we need some kind of liquid over on that side. And that was the purpose, of course, of our calcium hydroxide. And I'll address that in just a minute. All right, so I'm going to go back and we're going to take our sugar that we weighed out. I'm going to take that sugar and I'm going to dump it down into this 500 ml volumetric or 500 ml E flask that we had set up on this apparatus. I just took the cork off and I poured my sugar down on the inside. We also are going to add some water. So here you're seeing about 250 mils of water I decided to add in. And I'm going to give it a good shake. I want all of my sugar to dissolve. If my sugar's not dissolved in the liquid, then my yeast is going to have a harder time accessing that food stuff for itself. So I do want to make sure that it's fully dissolved before I go any further. Now I'll go back to my pasture salts and I top it off with some water. And as you can see, it cleared up pretty well for me. I mean, it's still somewhat cloudy, but it did clear up much more than what it was beforehand. And you can see this is kind of a misnomer. Don't go by this little divot. I don't really know what that is. But up here at the very top, you're going to see the liquid level there. All right, so I've got this graduated cylinder over here to the side. That graduated cylinder is there because my directions, I think, told me to measure out 30 milliliters of the pasture salts. So I took the pasture salts, I poured in 30 milliliters. That's how much I decided to use. Again, you can make your observations now of the pasture salts. Notice the way it looks in the graduated cylinder. I think it's much clearer now than what it was in the very beginning. All right. And then the directions say warm the sugar solution up. So warm it up to 30 degrees is what it tells me. That will help all of the sugar to dissolve in the water. And that's exactly what I did. So here I've got my Vernier LabQuest 2 device, which is my electronic thermometer basically. And I took the thermometer probe, as you can see over here on this side, and I dunk my thermometer probe down into that sugar water. And this is at 30 degrees. So I had to heat it up a little bit. And once it got to 30 degrees, I just took the heat off. And I gave it a few more swirls just to make sure that my sugar really dissolved. All right. If you get hotter than 30 degrees, then you can actually kill your yeast. All right. So if you increase the temperature by too much, the yeast go bye-bye. And if the yeast goes bye-bye, then you will not get any alcohol at all. So that's a problem that we always have to deal with, whether it's in a lab using yeast, or whether it's making moonshine up in the woods, or whether it's in your kitchen making homemade biscuits and homemade bread. If you kill your yeast and it's a yeast-based recipe, nothing's going to happen. That yeast produces CO2. That CO2 is going to start filling up your dough ball at your home in your kitchen, and that is what makes your bread very light and fluffy and airy. And that's where that term comes from. It's the CO2 that makes it airy and light and fluffy like a little cloud. All right, so the temperature probe is on the inside. Of course, I didn't keep it in here. Once it got to 30 degrees, I took it out. There was no sense in me kind of tracking or measuring the temperature after that point. And then I add the pasture salts into that container of sugar water. So that's what you're seeing in the picture here. I took the 30 mils of pasture salts. I added it to the e-flask that contained my dissolved sugar. That was at 30 degrees. And now I am ready to add my yeast. I'm doing it in the directions that the lab procedure tells me to do. All right, so here's the yeast. It looks a little weird, okay, and that's because of the type of yeast that we used. Yeast is yeast, though, for this procedure. It doesn't really matter. So here is a close-up picture of what the yeast actually looks like. So again, those are going to be little live creatures that are going to be doing some work for us, and that work is ethanol production. So I'm now going to add the yeast into that Erlenmeyer flask, and now all of the components and the ingredients for life to make ethanol is inside of that flask. So the addition of yeast goes in, the yeast gets dissolved up a little bit, they become active, yay! And they eat the sugar, and then they poop and pee out the ethanol. All right, so I shook the Erlenmeyer flask at this point just to kind of give it a good shake, make sure that things are dissolved that needs to be dissolved. Not everything went in solution, and as you can tell, the observations here from this flask, not everything is clear, not everything dissolved. I mean, you're seeing stuff float around in that solution and so forth. On the other side, now that this is activated, I'm going to put the cork back on it, and this is going to start producing CO2. So over on the other side, what you're seeing here in this picture is I'm taking that calcium hydroxide that was up here, that saturated solution, and I'm trying to pour only the liquid off. I don't want any of the sludge at the bottom. So only the liquid, the saturated liquid, is going to go into the test tube. And I'm going to fill it up. And of course, I want it over this part. All right. If I don't go over that part, then I'll never see CO2 bubbles that begin to happen in my solution. So I've got to go higher than that. And that's what I did here in the picture. So how high, it doesn't really matter. As long as CO2 is going over there and it's going to bubble and you're going to see it, then that's really all that matters. And the amount's not really important. Now, on top of this, we want to make sure that none of this goes anywhere, okay? I don't want this stuff to evaporate off. I don't really want to lose any of it. I don't want it to dry out and so forth. So we kind of seal it. We put a cap on it. And in the lab procedure, it tells you to add mineral oil to the top layer of this. Slowly add mineral oil, it says, and do not mix it. So here's the mineral oil jug that I decided to use in the lab. So this big F, of course, stands for Fisher Scientific, Fisher. So Fisher Scientific is going to be the label here, or the manufacturer name. And then, of course, our lot number is over here to the right-hand side of the label. You can see it here, but it's cut off. So I turned the bottle around and you got to see it right there. So there's the lot number and the manufacturer for the mineral oil. So I took some mineral oil. I just used one of our disposable plastic pipettes here up here at the top. And I just added some mineral oil slowly down the sides of this test tube. It told me in the procedure, don't really mix them. Just slowly add it. And whenever it tells me that, that's normally what I do. I just slowly add it down the sides of the glassware. I don't really just squirt it all over the top of that liquid solution. If I do, it begins to mix, and they don't really want them to mix. So by slowly adding it down the sides of the test tube, you're now seeing a layer that shows up right here. And that layer is my mineral oil layer, and that's staying on top. So there is my cap. There is my seal. So that way, when bubble, bubble, bubble begins to happen, it can kind of go up, and it can go up through this kind of process. And then this mineral oil will just kind of help stop it a little bit and slow it down, so it's not going to go too crazy on me. All right, so the beginning of the fermentation here, I've timed it and I've dated it for you. It happened on June the 1st, and it started at 2:30 p.m. Okay, so there's the time and the date of the beginning of the fermentation process. Now take a look at the observations here. The observations in that Erlenmeyer flask are probably something that the grade sheet's going to ask for. And then 30 minutes later at 3 o'clock, I go back and I show you an updated view of what this Erlenmeyer flask begins to look like. So again, you can make those observations if you want to as well. 30 minutes later again, I go back, and this time it was at 3:30, and now you can make an observational change for sure. So you can write those observations that you are seeing into your lab book. And then next, the observation of the vent. This is what it begins to look like. So as that solution at 3:30 begins to do what it's doing, over on the right-hand side, you begin to see what that's doing as well. So if you look, you see a little bit of solid that's getting precipitated down here at the bottom. We're assuming, hopefully, that CO2 gas is coming out of the stem, and if it does go up, that mineral oil will kind of help stop it, keep it in solution for a little bit. 30 minutes later, this time at 4 p.m., this is what the solution begins to look like. I did a very close-up of the liquid, not just the foam that's up at the top. And then for that particular day, this is the last time I've captured the observations. So at this point, I just left it to ferment, do what it needed to do on June the 1st. Okay, so then I go back into the lab on June the 3rd. So a couple of days later, and this is what the Erlenmeyer flask looks like at this point. So June the 3rd at 11:30 a.m., we can now go back and we can write more observations of what we see in that flask together. And you can write that into your lab book if it wants you to write that into your lab book. And then I also took a picture of what the calcium hydroxide looked like as well. So keep in mind what that test tube looked like in the very beginning, and now this is what it begins to look like. So once again, I told you, think about bubbles, think about the precipitation that's happening at the end, the purpose of the mineral oil, and so forth. So observations of June 3rd, this actually looks pretty good. At 11:30 that morning, that's what it turned out to be. So my fermentation was still not finished. I've only really let it ferment now for 2 days, and it tells me at least 5 days. So when did I actually go back to the lab and pick this up? Well, this was on June the 8th. So on June the 8th, I go back at 11 o'clock a.m. that morning. I took another picture of what that flask looked like. So this is the observations now of the Erlenmeyer flask that had the fermentation on the inside. So once again, if you need those observations, you can make them and you can write them down into your book. As well, over on the test tube side of the house, Once again, these are the observations or changes that you could write about as far as that end as well. So same time and same date, June the 8th at 11 o'clock a.m. that morning. So if I took a picture of the overall, what did it look like on the final day before I began to do more things with it? This is what it looked like. All right. So fermentation setup, this was on June the 8th at 11 o'clock a.m. So this is giving you both pictures at once to show you that I didn't really change anything. I didn't tamper with anything. It looked the same as what it did on day one when we began fermenting as far as the setup goes. All right, so there's your overall observation. All right, so now it's my job, because what I have in this beaker is now dead yeast, and I don't want it, right? I also have water that I don't really want. I want just the alcohol, and that's it. And then I probably have unreacted sugar and so forth, and past year salt remnants. But at the same time, I also have ethanol, and that's a capital E, lowercase t, OH, and that is the short-handed version of ethanol. So I need the ethanol out of there, and that's going to be the purpose of the next part of the laboratory procedure. So one of the first things that they tell me to do is to filter. And the reason they do that is because this yeast is pretty big, and I want to get rid of it. But at the same time, this yeast, there could be small little chunks that are going to be in there that's going to go through my filter paper. So the directions in the lab book is going to say, take some sea light. Well, we don't really have any sea light. That's too fancy for us. We don't want to spend that much money on sea light. So what we do is that we use a substitute, and that substitute is called diatomaceous earth. They're dead little sea creatures. That's what diatomaceous earth is. If you look at these under the microscope, they look like little sponges. Okay, they're very rough on the outside. They're very rigid. They look like Swiss cheese sometimes, and some of them are actually kind of pretty. But this is diatomaceous earth. So what we do is that we use this as what we call a filter aid. So a filter aid does just what it says that it does. Okay, I have a Buckner funnel that I'm getting ready to filter this stuff in, and then I have a piece of filter paper in the Buckner funnel. So if I add the sea light, which is a brand name, or if I add the diatomaceous earth, then this will kind of cake up on the piece of filter paper, and I don't want too much of it. If I do, then nothing will ever go through this piece of filter paper. Okay, I'm going to stop it up so much that nothing will go through. It will be completely clogged. Think about your clogged toilet at home. You don't want that to happen, do you? So the filter aid goes through, crams some toilet paper down into the bottom of this bowl, and then it only allows certain things to go through at that point. Okay, so it stops up the pores of the filter paper. That's why we use it. So anything extremely smaller than the pore size typically has a harder time to get through, and then only pure liquid really will escape through the diatomaceous earth and through the filter paper into my Erlenmeyer flask that sits down below. So the lab directions are going to say weigh out 10 grams. Well, folks, I didn't, because I know that my Buckner funnel, and from past experiences, 10 grams is way too much. What I'm getting ready to actually weigh out here is actually going to be too much as well, but I did it. So here's the tiered balance for the sea light or the filter aid. And then what I do is that I put the flask on it, because this is what I'm going to make my slurry in. And notice the flask weighs 192.1866. I don't really do anything with that mass because, this is not a final product or anything. But again, I write down weights whenever, and if I don't use them, I don't use them. And then I tear it out the balance one more time. So when I tear it out the balance, it now reads 0.0000, and I add the sea light directly to that Erlenmeyer flask. So the sea light here that I used was 4.6373 grams. Once more, the lab tells me 10, and that's overkill. I don't want 10 grams. I'll be here for weeks waiting on that stuff to filter, and I ain't doing it, and I know that you don't want to do it either. So I used less than half, really, and I should have actually used a little bit less than that in order to make this process a little bit faster. All right, so I go back to my filter paper drawer. I bring out the filter paper. It's a Wattman filter paper that we've been using over and over and over in every single Buckner funnel that we have. And then I added water to that Erlenmeyer flask, deionized water, DI water is what I added, and I just really kind of made a slurry out of this mix. So just give it a good swirl. Just not all of it will dissolve. It's not supposed to dissolve, okay? You're supposed to get a slurry. You're supposed to get a sludge that will begin to pour out of this Erlenmeyer flask. So you can make observations of the slurry if you want. And then here I'm ready to pour it. So this is me after I gave it a swirl for a couple of minutes, I would say, and I'm getting ready to pour this slurry of sealite or diatomaceous earth into my Buckner funnel. All right.
All right, guys, so in this step, we are fermenting alcohol, and we're getting ready to separate the alcohol that we fermented. And in this flask, I have the diatomaceous earth, which is our substitute for the sealite that it actually talks about in the lab experiment. So what I'm getting ready to do is I'm going to pour this slurry through the Buckner funnel. And when I do that, all of the liquid's going to go through, and of course I don't want to save any of this liquid because my alcohol is going to end up going into this flask as well if I do. So I'm going to have to switch this filter flask for a new one after I do this. But the purpose of this step is to send the filtrate or the filter aid through the Buckner funnel, so that way I can get a solid that is going to be staying behind on my filter paper from up above. The reason is that the yeast is very, very tiny, and I don't want it to go through the pores of the filter paper. And as you can already see, it's really slowing down on me, and that's just normal, that's routine. So now all of the larger pores of the filter paper are going to be stopped up, and it's going to be stopped up by my diatomaceous earth. So after I give this some time to filter through, I'm then going to take my alcohol, which sits over here to the left-hand side of me, and I'm going to slowly pour that through this Buckner funnel as well. But before I do that, I'll switch the filter flask that sits down below.
All right, folks, so I think you get the idea. You know, this is just really stopping up a piece of filter paper that has too large of a pore size for me, and I don't want to go and be crazy and spend, you know, hundreds of dollars for specialized filter paper that will have those really tiny pores on there for me. So here's the filter aid that's added. You can kind of see it caking onto the filter paper. You can also see somewhat of a mound that's showing up in the center, and that's what you're seeing here. I'll just outline it with a dashed line. That's a mound of filter aid or sealite that's getting kind of clustered up in the middle of this setup. So after I poured the sealite or diatomaceous earth all the way through and filtered it, this is what's left over in the Erlenmeyer flask. And I'm okay with that because, again, this is not about transfer. It was just about coating my filter paper. I don't really care that I had stuff that left behind like this. I mean, I felt pretty good about the surface of the filter paper, knowing that it had a pretty decent amount of diatomaceous earth already on it. If you look at the water from the filter aid, it's now clear. I mean, think about what this looked before filtration and now after filtration. So the filter paper is seated the proper way. It's covering up all the holes, and the filter aid is now covering up the filter paper, and that allowed my water to go through, and it does look pretty clear to me, right? Depending on what was in this Erlenmeyer flask, I like to use the same one over and over and over. I know that's a shame, but that's what I do. Depending on what was in there before, I mean, this looks pretty clear to me. All right. So then I took, like I said in the video, I took that Erlenmeyer flask away because that had water in it, and I don't want my ethanol to be contaminated in any form or fashion. So I took this filter flask away and I switched it with a brand new one that's down here in the bottom. Now, I don't really have to do anything to that filter flask. I'm not weighing anything. That's not my final ethanol product or nothing. So I didn't take a weight, and that's why I didn't take any measurements of it. I just switched out for a new one, and we're just going to filter it. That's as simple as what it's going to be. So here's my alcohol mix. I go back to that fermented Erlenmeyer flask that had my yeast and my sugar and my sludge and everything else in it, and this is what it looks like, so that way you can make observations one more time. And I begin to slowly pour that solution through the Buckner funnel. I slowly pour it because if I just dump it all in at once, then this is going to be even harder for this filter to do its job, because now I'm stopping it up even more. So if I go really, really slow with this, it tends to go through a little bit faster. And again, that's good for me, especially if I'm pressed for time in the lab. Down at the bottom, this Erlenmeyer flask, as you can see, I'm getting some liquid that's down here on the bottom. All of my yeast is staying up here with all of the other sludge and crud that I don't want. And pretty much the only thing that's going through here, I hope, is the ethanol and the water mixture that I have with some dissolved pasture salts. All right, but ethanol and water mainly is what's going to be there. And maybe some unused sugar that's still dissolved up. All right. One of the things I wanted you to take a look at was the filtrate. So the filtrate is the liquid that goes through the Buckner funnel. Notice the way that this looks. It's not really a true liquid that's coming through there. All right. That liquid is really a foam at this point, and that is a pretty common thing that I see whenever we use diatomaceous earth. The reason for this foam is because we are using air to suck everything through the Buckner funnel, and this begins to increase the pressure of the system. And when my pressure begins to increase in the Erlenmeyer flask, I begin to see some of the liquid to maybe just get incorporated with a lot of air, and some foam and some bubble begins to happen inside of that flask. All right. Down here at the bottom, you're seeing that the liquid solution as well is getting foamy, and it's going to get foamier. So as we begin to filter through, and as we begin to keep pouring our water alcohol mix, this is something that's very common. I mean, we're in the world of ethanol and fermentation here, and what I like to relate this to is, think of a beer, right? If someone pours you a beer, you see all the foam that's on top if they pour it the wrong way. Some people don't want that foam at all. But it's very kind of similar to what you're seeing here. This also begins to smell, and it begins to smell like a brewery. So if you think about a place like Front Street Brewery, or maybe Ironclad that's downtown, you go into those places and you smell kind of that yeasty smell, odor, that's a very strong beer smell maybe. That is what this smells like. It's identical to it, because that's really what we're producing here, right? We're using yeast and we're fermenting, and this is just part of that natural process. So that is the odor that we're beginning to smell. Over time, as I begin to filter this solution through the Buckner funnel, this liquid begins to go through a little bit slower, and that's because the filter aid is up on top, and we are slowly filling in the pores of that filter paper even more so as we keep pouring solution through. So it does slow down quite a bit. I'm not giving up on it though. I'm continuing to pour that solution through until I can get as much as possible through it. All right. Here's another picture as I continue to pour. The foam again is continuing to come from the Buckner funnel. The foam is continuing to stay behind in that liquid solution. And this is what happens toward the end. So this is not the end exactly, but toward the end, what you're seeing is a pretty clear solution here. You can make those observations that you want. It also looks like we're kind of at the 300 mark here, and I see a little bit of foam that's on top that's beginning to settle out. I just let this continue to run. I just let it kind of continue to sit and do its own thing. And then when I come back to it, because there's no more for me to pour through, I come back to it and this is what begins to happen. So the foam layer does disappear. And now we see we are greater than 300 milliliters in total in the Erlenmeyer flask or the filter flask that sits below. All right, so now this is the observation of my ethanol water mix before the next step, and that next step is going to be fractionation. All right, so that's what we're getting ready to do now. So there's ethanol inside of here. Okay, not a lot, but there's ethanol in there, and I want that ethanol out. And the way that we do this is we go through the process of fractionation. All right, this is going to help me clear up and separate components, get really pure products, and hopefully I can beat out a place like the ABC store and Everclear based on the proof that I end up with in the lab. So what pieces are required for my fractionation? Well, piece number one is going to be a ring. Okay, I need some type of support, and that support is going to help hold up what we call our heating mantle. So I need a ring with a clamp or a clip that will clamp down onto the ring stand that we're going to be using. All right. Something else that I need is the variac transformer. Again, you've seen this in other labs, and it's going to come back to us. So I bring out the ones that I know for sure are good, because these are our newest ones, the red ones. And that way I can feel really good about it when I plug it up. I know I'm not going to waste my time. The heating mantle gets plugged into that variac transformer. The heating mantle is what you see here, the silver plate. Some of these older ones actually have a pretty nice plate that sits on top of the mantle. So you can see the fabric cushiony stuff here in the center that this boiling flask is nestled down into. And then this metal ring just provides me a little bit of support for that heating mantle. So sometimes I like to use these depending on what we're doing. They're a little bit older, but they work just as good, if not better. All right, so there's the heating mantle and the round bottom boiling flask. So round bottom boiling flask, or RB flask, is also okay for people in a laboratory setting. They know what RB means as long as you make an indication of that in your lab book and say RB equals round bottom, then they'll know exactly what you mean. All right. Another component with the fractionation is this thing called a Vigru column. So the Vigru column is going to be attached on top of my boiling flask, and this is the column that begins the separation. So what will happen is that ethanol has a lower boiling point than water does. So ethanol will begin to travel up this tube a little bit faster and a little bit better. And then what happens is that water begins to maybe evaporate off as well. And over time, they begin some separation between each other, because this is a pretty long path for it to travel up and then eventually over into my condenser. So this takes some time. It needs to have kind of, the ethanol is really having a head start, and this water, if it wants to catch up, will have to move up even faster. And there's just no way for it to do that unless you just really crank up the heat and boil everything over at one time, which of course we don't recommend. Here's another picture of what we call a West condenser, and the name does what the name says it does. It condenses. So this piece is going to go to the side, and this is going to start condensing the vapor of ethanol back into a liquid of ethanol that we can then collect over on the other side. Because we're using a lot of glassware, because we're using a lot of pieces and attachments, I also need to bring out a couple of the clips. And these clips, of course, are going to go on the joints of the glassware. And it will just help hold those pieces of glassware together. I mean, that's the purpose of the clips. Now, it's not going to prevent it. I mean, they can still be separated even with a clip on it. But it will help hold them in place as long as you're not doing anything crazy with them. All right. Over on the other side, I told you that we're eventually going to get ethanol to be drip, 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 drip out. And this is what we call a drip adapter. So this is going to go onto my West condenser. And my West condenser will change the vapor to a liquid. And then this liquid's got to go somewhere to go. So we like for this to be orderly. So the liquid is eventually just going to go down into my drip adapter. And then it will be directed into some type of collection flask. All right, so the collection flask that I decide to use is just going to be simple old Erlenmeyer flask. And I did 2 of them. The reason that I did 2 is because one is going to be for any early contaminant that I might see in my fractionation. So if I begin to see liquid dropping over before the boiling point of ethanol, then this is bad news for me. That means that this could be something like methanol, which I do not want and can cause me to go blind. So I'm going to get rid, this is just waste. I'm going to get rid of any of that if it shows up. Sometimes it does and sometimes it doesn't. But if it does show up, we dump it, we get rid of it, we don't include it. And then that way I'll have a backup. And this backup will simply be switched for the first one when my ethanol finally decides to start distilling over. That way I don't have to turn my back. I don't have to go and dig. I don't have to fumble through drawers. Everything that I need is right then and there, up front and personal for me to use. So one more thing that we have to kind of pull out of here, because I've just talked about temperature and boiling points, is going to be a thermometer adapter. So this thermometer adapter is a piece of glassware that fits in our joints of our glassware, and there's just a simple thermometer that goes down straight through the middle. And this thermometer bulb needs to be in the proper location. And that thermometer bulb will have to be at a joint of the Vigru column. And this is going to provide me temperatures of the vapors as they begin to distill over. So all of that said, this is what the combined apparatus looks like. So I've got my variac, and my variac is here to the left. And then I have a heating mantle. The purpose of the heating mantle is to provide the heat. And the purpose of the variac is to control how much. Remember, this is a stove eye. So this is your low, medium, and high setting. Okay? That heat will be delivered to the round bottom boiling flask. This will begin to evaporate the ethanol, and it will turn it to a vapor, and up it goes through the Vigru. When that ethanol hits that thermometer bulb, that's right there, and look, right there's the joint, right there's the bulb. When it hits that thermometer bulb, my temperature skyrockets. And it goes to the boiling point of that particular vapor, and hopefully it will match ethanol's boiling point. Well, that vapor will eventually make its way over here because it can't go up. It's stopped, right? I mean, we got a thermometer adapter up here. It can't escape. So it eventually goes back down and it pushes through the west condenser, and the west condenser has water that runs in and out. Keep in mind that in always goes through the bottom and out always goes through the top. So this hose leads from my faucet, and this hose goes down into the drain. This is going to circulate cold water, and my ethanol vapor will condense, and that ethanol vapor will go through my drip adapter, and the drip adapter directs it into my Erlenmeyer flask, which sits over here to the right-hand side. So there is the fractionation setup, folks. That way you can make a drawing of that in your book, and that way you can study for that for the final exam at the end of the semester. All right, so I'm going to add my filtrate here. This is my water and ethanol soup mix with no yeast now at this point. So I just dump everything in there, and I go over to my variac, and I turn my variac on. You can't really see it in this picture, but this needle is pointed at 70. All right, so that's the setting on the variac, and that begins at 12:15 on June the 8th. So there's your date and there's your time. All right, so in the next slide, what you're going to see is a video, and I'll play this video that just kind of highlights and showcases the distillation setup again.
All right, folks, so this is the setup for the fractionation of my alcohol that I have made in the lab. So I've got my variac transformer here. I've had it set about 70 to 75, and I've just now turned it on here in the very front. So it's not even yet warm, but at least I'm giving you an image of what the distillation is going to look like. All right, so from the variac transformer is going to be my heating mantle, and that's what you're going to see here. And my heating mantle will have my alcohol solution in it that I need to distill. So I need to purify it up, and this is going to require me to boil it. All right, so in the boiling flask, I have my ethanol plus all of the water that came from the fermentation. I have a clip that's going to be here, and that clip is going to lead into what we call the Vigru, or the fractionating column that you're seeing here. It is a super tall column, so it's going to take quite a bit of time in order for me to distill it up and over. But the reason that this is so long is because I want to make sure that I have a pure, clean product in the very end. What you're seeing now in this image, or at this piece of the setup, is my thermometer adapter, and notice that the tip of my thermometer is actually right here at the joint, and that's where I want all of my thermometers to be if I'm expected to record temperatures and so forth. So from that thermometer you can see a thermometer adapter, and then the thermometer of course goes straight up so I can read that scale when I need to and record those temperatures as it begins to distill off. I see another clip here, and then that clip is going to lead into what we call a west condenser, And this West condenser, of course, condenses all of my ethanol vapor back into a liquid. And I've got water hoses that run from the right-hand side to the left. So in the right-hand side, what you're going to see here is the water in, and then over here is my water out. From that point, after it condenses, I have another clip with a drip adapter, and that drip adapter is going to start dripping my ethanol into this Erlenmeyer flask that I have here. It's 125 ml size. Quite honestly, I'm only going to get a couple of milliliters of alcohol from this process. It's not a very large batch or a large recipe, so that is actually too big almost in a way, and I could simply go to something like a 25 or a 50 ml Erlenmeyer flask if I wanted to. Alright, so what I have here is a backup. After that flask, I've got another one that's sitting here for a backup. The reason is because if I start seeing drips here very early on, that's probably due to some methanol, and I want to get rid of that contamination. So I've got a backup just in case I need it. I might not see any drips, but just in case I'm in the process of, I don't want to go through and try to rumble, trying to dig up another Erlenmeyer flask, and I've got one ready. Alright, so there is the fractionation setup, and this fractionation setup is going to hopefully give me 190 proof or higher alcohol from this process.
Okay, so June the 8th, 12:15, I turn the heat on, and this is what it begins to do. So again, you can make those observations as you see fit. And then what I decided to do to help this process out is that we insulated the Vigru column. This is not unheard of. I just took some aluminum foil and I just wrapped it up and down this Vigru column, so that way when this stuff gets hot, it can stay hot and I don't really lose any temperature through the air currents that might be in the room and so forth. Otherwise, this process could take much longer. The drawback here, though, is that the aluminum foil, because it does insulate, can make things boil off faster, which means that you can get more of an impure compound if you are not careful. So this is something that you want to watch out for. The aluminum foil is great. It does save you time, but it's very easy to distill off things and to have a contamination issue because more than one thing is coming off at one time. All right, so as I begin to heat, I just go back and make some more setting changes. So at 12:20 on that same day, I go back and I change the setting on the Variac from 70 to 85. And then I just keep a look at my temperature gauge. So I see my temperature of the first drop at 12:39 p.m. All right, so 12:39 p.m., about 20 minutes after I crank the Variac up, I see my very first drip that happens on my receiving side. All right, so that means this process is now beginning. My fractionation is now beginning, and that's the temperature of the vapor as it begins to drip. All right, so here's a close-up picture of the drip adapter leading into my Erlenmeyer flask or my collection flask, and this is the time that I shout, "Eureka! I'm getting some alcohol." All of that was not for nothing. All right, so I'm just going to continue to let it drop. I'm just going to let it go. I'm going to let it do its thing. I'm going to just keep collecting. I really didn't see anything that happened before the temperature of 79, so that means there's no really other contamination like methanol that's in the solution. And another thing that I always look for is the West condenser side. So notice the way this West condenser looks. As you can see on this side of the picture, this is pretty much clear, okay? And then over to the left-hand side, this is very watery, it's very bubbly, it's very cloudy and smoky, and that's because vapor is getting filled up in this West condenser, and condensation is happening all around my West condenser in this section, and that's very good. The issue here, though, is that in the West condenser, you often see a puddle that begins to form right in here at this little bevel. So at the very end of this, if you really want percent recovery and you want that extra oomph in your volume or in your mass, then you really do need to take this apart and you need to tip this up. That way this little puddle right here can flow down through the West condenser and go into your receiving flask. All right, here's a close-up picture of the aluminum foil that's pulled back at the joint area. And if you look at this joint area, you also see condensation that's beginning to gather right in here as well. So once more, notice the position of the bulb. The bulb is basically right there at the joint, and that's typically where you want it to be. Now, depending on your thermometer, right? Thermometers are made different ways, so they might want you to go a little bit further down, but on this particular thermometer, the bulb needs to be at the joint. All right. Another thing I want you to pay attention to is this number. Okay, the number is 2440. Well, that's the size of the joint. Okay, so 2440 is basically like the length and the width of the joint area that all of our glassware is made out of. And all of the glassware in the ChemTech lab or in our laboratory facility is going to be 2440. We use normal standard size glassware, and we do not use micro scale crap that's out there in the lab. That stuff is just too tea party for us, so we just trash it, we kick it to the curb, and we use standard size glassware for this purpose. All right. Over time, you can see this condensation getting more and more dominant. This is something that, very easily seen at this point now. Throughout the heating period, this is something that I would expect. And the more or the closer that the condensation gets to the bulb, then this temperature will begin to jack up after that part in time. As my ethanol is getting distilled over, you can see the liquid that's down here in the very bottom. That liquid is very clear. That looks like alcohol, what alcohol should look like, right? But it still does have an odor. It still does have that kind of yeasty, smelly odor that's associated with it. And that's something that's very common with this process. It doesn't necessarily go away too well, and that's just something that's expected. All right, so here's another video on the distillation.
So here is my ethanol sample, my pure blue moonshine right here, okay? So it's still distilling, that's why you're seeing it move. It's still dripping from the fractionation column, but you can see how much I have so far. I mean, I'm not even at the halfway mark between the 0 to 50 yet. So I've got less than 25 mils. I might still have a little way to go. But up here you can see that my ethanol is distilling off. You can see all of those drips that are happening. Each one of those drips is liquid gold to Granny from the Beverly Hillbillies. And then as I travel over through the West condenser, you're starting to see a little bit of cloudiness to happen right in here. And you can see that liquid actually condense down and turn to a liquid so it can make its way to my Erlenmeyer flask. All right, so there's the condensation from the fractionation column, and my condenser is doing the job that a condenser should do, and it's all due to the cold water that's circulating through that piece of glassware. So I'll continue this process on, and this process will stop when I see my drips really slow down after a certain point in time.
All right, so one of the things I wanted to mention in that video is the speed at which those drips were happening. Notice that they were not very crazy, okay? They're not very fast. I was giving it some time, and you're going to get a better product when you decide to do that. So don't rush it. Be patient. Like I've always said, be patient with this stuff, and you're going to end up getting really good products and really good yields if you do. So I'm just going to continue to heat because I still see drips, right? I'm still seeing drips over on that receiving end. I'm going to continue to heat this stuff over and over and over until those drips slow down or my temperature spikes, one or the other. All right, so here's just another image of the West condenser. Again, it's still cloudy. I'm still getting condensation. I'm still getting drops, and all of those drops are ethanol. Inside the Vigoroo column, you're also going to see these little, what I call teeth inside of those columns, and this just gives some more surface area for the vapor to cling to, and you're seeing drops that are right here on those teeth. So it just helps the separation process a little bit better, and I can track the drips in the Vigoroo in order to track where the vapor is going to be located. The top of the Vigoroo, again, I see a lot of condensation around the joint. That's a very good sign that my stuff is still coming over. I just want to be careful, and the reason I say that is because as I'm getting closer to the end of the fractionation, well, water could be making its way up as well. So water condensation could be happening, and if water condensation goes up and into the joint, then all of a sudden I get a contaminated ethanol mix, and that contaminated ethanol mix with water is actually going to lower my proof. It still tastes good, but it's going to lower my proof. All right, so I'll just continue to heat, and I'll continue to let it drip, and I'll continue to take a look at the thermometer and the temperature and the condensation levels of my Vigoroo to make sure that everything's going as planned. All right, so here's another picture of the joint. This is a time, though, that I'm capturing for a reason, and that's because at this point in time, condensation made its way up to the bulb, and that bulb kicked back a number to me, and this is the temperature of that thermometer at this point. So this is over the boiling point of ethanol. So you can make that observation the way that you want to make that reading an observation, but this is over the boiling point of ethanol, and there is a possibility that I am running the chance of getting water at this particular point. So I begin to stop it. All right, I stopped the heating process. This was a sign that I was now finished, and I just allowed this thing to cool at room temperature, okay? I just kind of turned the knob on, flipped the button off, and I walked away from it. So I stopped this process at 124 on the same day that I started it. So as this begins to cool down, okay, I then go back to the balance and I tear it out, so 0.0000, and I grab a container. I label this container as number 1 because, quite honestly, I'm not sure if I can fill this container up or not. If I do, then I'll need a second one. So I've labeled this container as vial number 1, and then we get a weight. So the mass of that vial is 29.9574. So just in case I need it, I did a second one in case I filled the first one full, and the mass of the second one is 29.2430. All right, so notice I weighed it with the masking tape and the handwriting number on it. If you add this later, that's weight that you are adding in, and that weight can contribute to a percent error miscalculation. So you want to be careful with that. All right. So the condensation, there it is. I know it's there. I know that there's a chance of water getting into this mix at this point. Hopefully not too much has gotten into the mix. But again, I did turn it off and I am letting it cool down. So I transferred all of the ethanol that was in that receiving flask into vial 1. And this was the mass of vial number 1, 53.9175. And I did fill it full. So I did have to use vial number 2. And vial number 2 ended up having a mass of 32.6078. Here I took a picture of a close-up of the solution. So hopefully that's pure moonshine. And we're getting ready to figure out the proof. And we're getting ready to figure out if, in fact, it is moonshine or AKA ethanol. All right, so how am I going to do this? Well, the first thing that I do, the directions tell me to take a density. I need a density of that solution because I need to use a calculation with a density. So if you remember how to use a volumetric pipette, I grabbed a 1 milliliter volumetric pipette. And on the volumetric pipette, there is a line that is etched. And that line is right there. You can kind of see it marked. And I need to suck up solution through the volumetric pipette using a bulb, not my mouth. Using a bulb up to the line where the bottom of that meniscus is at that etching. And that represents 1 milliliter exactly. So I went to the balance and I teared out another container. And on that balance, I delivered 1 milliliter of liquid. And this is the mass of 1 milliliter of liquid. So the density calculation, the density is grams per mil, right? So with the density calculation, this is how many grams per 1 mil of solution. And that is why I used a 1 mil volumetric pipette for this purpose. I could have used a 5, I could have used a 10. I mean, it wouldn't have mattered. My mass would have been higher, my volume would have been higher, so I would have just taken my mass divided by 5, or my mass divided by 10, or the mass divided by 25. Whatever amount of volume I decided to use, volumetric pipette-wise, that's what I would have divided by. And for me, I don't want to do all the math. So I use the little tiny 1 mil volumetric pipettes, and I'll just deliver 1 mil of sample onto that container, and I get a mass of it, and that will give me my density. All right. So there's the density that you'll need in order to calculate proof, and there is the proof, basically, that you would need in order to prove that you did make moonshine or ethanol as pure as possible. All right, the other thing that we're going to do in the experiment is use the FTIR instrument. And the FTIR instrument is going to stand for Fourier Transform Infrared Spectrometer. And the purpose of the FTIR is to analyze a sample, and based on what we call the fingerprint of it, it will tell me what that particular compound is. So imagine this as your fingerprint, right? If you got arrested and you were taken down to the jail or the magistrate's office, and they processed you for booking, and they put your finger basically on a fingerprint machine, well, that's very unique to you, isn't it? So not too many people will have the same fingerprint. Well, folks, this is the fingerprint of compounds. This is what it kind of reads. So all compounds will be different, and the FTIR will pick up the fingerprint of that particular type of compound, and it will tell me exactly what's present, at least in the largest amount. Okay, so the FTIR instrument, that is what that stands for, FTIR, and that's why we would use it. We simply use it to ID unknown compounds most of the time, whether they're liquid or whether they're solid or whether they're gas. It doesn't really matter. It can suit all three. All right, so this is the way that I start up this instrument if this is the first time that you've seen it. So I go to the computer, I start the computer up, of course. There's an icon on the computer screen, and that icon is called Lab Solutions IR. This is a short-handed version of the software that will save me a few steps. If you double-click this Lab Solutions that's down here, then Lab Solutions will also give you the same prompts, and it will get you to where you need to be, but there's a few extra steps along the way. So the Lab Solutions IR is the shortcut version, but both of these will actually work. So when I double click Lab Solutions Infrared, this is what shows up. It says Lab Solutions, right? And then there's no username or password that we use. So we just hit OK, and then a confirmation screen will pop up, and it will look like this. That confirmation screen is going to give me a few options, and those options are going to be post-run, spectrum, quantitation, photometric, time, mapping, and macro. So what I want to choose is the spectrum because we want the fingerprint, and that is called the spectrum of the compound. So I'm going to click the icon that says spectrum. When I do that, that screen goes away, and we get this prompt, something that looks like this on the computer. Everything will be grayed out. Pretty much everything will be grayed out except this instrument button. So I'm going to click the instrument button, and when I do, I'm going to click initialize. Even notice that all of these are grayed out as well. So I need to initialize the machine first before I do anything with it. And that's always our first step when we start the machine up when it's asleep. If someone else has used this already and the machine's active, I don't have to do it. But if I'm the first one to get over to the lab and turn this machine on, this is the first thing that I have to do every time. So it's going to take maybe 2 to 3 minutes. It initializes. It just makes sure that all the gears and things work inside the machine and that the software can talk to it. And then you will see these 3 big green buttons that will show up here on the left-hand side. All right. Before I scan anything at all, I need to think about a balance. One of the first things that I do is tare, right? I need to tare the balance and make it read 0. Well, that's the purpose of the background scan here. So before I run anything at all, I'm going to have to press background scan in order to do this. Now, before I do that, though, there is an attachment that needs to go on the inside. So after I initialize it, After it confirms that the machine can actually work, I then need to put my what we call ATR attachment on the inside. So ATR stands for attenuated total reflectance. And this is the piece that we are talking about right here. These others are just supplies and consumables that we use for a different reason, but this is the ATR attachment that I need to take a look at and that I need to use. So this allows me to load my samples up very easily. I don't really have to worry about what we call salt plates. You'll learn about that much later on. This just really requires a drop or two on the surface of a plate, and then I hit run. That's all sample prep that's going to be involved in this process. So I like the ATR, but the ATR is also very expensive. I mean, you're looking at $18,000, $19,000 here because it runs off of a synthetic diamond in order to work. So here's the FTIR ATR attachment. So I don't need this attachment for the machine to work, but it makes my life much better, much easier. And this plate is what will end up getting my sample that I begin to analyze and that I begin to run. All right. So here's me taking it out of the box and a close-up picture of the ATR. And then I'm going to place that ATR inside of the instrument. So I've opened up the front cover, and then when I've opened that up, there's a platform that is made for the ATR. I just sit that onto the platform, and there's a screw that's right here in the front, and I just tighten that screw up. Now that the ATR is in there, I then can go back to my software and I can hit background scan. When I do hit background scan, I'm going to see something that looks like this. All right, at the very end of this process, and this is normal. This is what I want to see, and it should take this shape every single time. Again, I'm blanking it out. There is some signal that's involved, and it's trying to correct that signal with my background scans. So if it did not get background the proper way, you're not going to get the proper infrared spectra in the very end of this process. All right, so here's another slide that has a video, and let me play that for you.
If you've had one of our classes before, you know what this instrument is. This is our FTIR instrument, which stands for Fourier Transform Infrared Spectroscopy. So I'm getting ready to put a drop or two of my distilled ethanol onto this instrument, and hopefully this instrument will tell me that it is ethanol before I decide to drink it. Alright, so this is just a way that we can identify a compound in a laboratory. This instrument is connected to a computer. You can see that it's running something right now, and the only thing it is running is a background scan. So I'm not running anything on it at this point. It's just really the ATR attachment, which is what you're finding inside of the instrument. And that ATR attachment right now is blanking itself out. So think of this as a tare function on a balance. Once this gets finished, I'll put a drop or two of my sample onto the instrument, and I will use the software in order to data match it. So more pictures to come, but this is the FTIR instrument that we will be using to identify, hopefully, the ethanol that I have made in the lab.
Okay, so after that background scan is completed, the screen will actually change. And it will change into just a normal confirmation screen that looks like this one here. But up at the very top, you're going to see this big button that says measurement. And that measurement button will become active. So I need to go up and I need to check that measurement button. I need to press it. So I'll click on measurement. And when I do, it will take me back to the home screen with those three big major green buttons, and that's what you're seeing up here at the top. All right, so this sets me up to get ready to run a sample. Now when I do run a sample, I'm just going to take a disposable pipette. Typically I use glass. That's because organics like to eat plastic, and I never really like to use those disposable plastic ones unless I know what type of organic that I'm using. Ethanol, not a big deal, but I normally gravitate toward glass when it concerns the organic compounds. So I suck up some sample, into that disposable pipette, and I just add a few drops. That's all it's going to take onto the plate of that ATR attachment. So a few drops, just enough to cover it up. That's all that you need, and you're done. That's as difficult as the sample prep is going to be. All right, so on the computer screen, I now go back, and this time instead of going to background scan, I'm going to go to sample scan. So I'm going to click sample scan, and when I do that, this instrument begins to scan the sample, of course, and that's why it's called sample scan, right?
So you're seeing my drop of hopefully ethanol on the ATR attachment, and I'm now currently scanning it. And here on the computer screen, you're going to end up seeing a FTIR spectrum that begins to show up. It is currently still running. It actually runs this 45 times, and it does an average after that. So that's what I'm currently seeing on my computer screen, which looks pretty good to me, just because I know what ethanol is supposed to look like on the FTIR. So I'm going to continue to let this run, and if at any point in time I see my sample over on the FTR begin to evaporate, I'll just add another drop or two, and I'll continue the read and I'll continue the scans.
Okay, so this is a screenshot of it actually running. So it's not really finished yet. I know it's not finished because I see the three big, what were green buttons up here at the very top, and then down below I see the stop. So this is in the middle of it actually running and gaining all of those FTIR spectra that it will then average and give me one fell swoop of one spectra that represents all 40 some that it does. I know that it's finished when those three big green buttons and that stop button goes away up in the top left. This up here at the very top is basically the match that it was the closest to, and then down here at the very bottom is what we actually got for our spectra. So that's why you're seeing two of these. One is basically it, and the other one is a very close match that it has found in the database. But I need to confirm that I actually do want it to do a database search, and at this point it doesn't really know that, right? It's just basically popping up my scan and saying, hey, here you go. And then, by the way, up here in this little tiny box, well, there's a spectra in our database that does match it pretty well, but you're going to have to confirm it, and you're going to have to tell me that you actually want to do it. So the way that we do that, up here at the very top, you see this icon that says search. So here I'm going to go up, I'm going to press search onto the software, and then over to the right bottom side of the screen, look at my computer monitor. It's right there. There's the time and date stamp. On the bottom right hand corner, it's going to show up Spectrum Search, and I need to click that Spectrum Search. That way I can tell the software that I do want it to cross-reference this in its database. When it does that, this screen will pop up, and what you're seeing is an entry that now sits below. And this entry will give me all possibilities that that compound maybe can be. So it doesn't do one. It will give me like a top 20, and it will say we're pretty sure that it's one of these 20 that we are reporting back on this report. If I zoom in on that report, what you see in the very top in line number 1, ethanol. So this confirms to me that that liquid that I distilled off was in fact majority ethanol. Otherwise, this FTIR would not be able to identify it, and it would have told me what exactly it would have been. Even if it was water, water has an infrared that it can confirm, and it will say, no, you don't have anything other than just water. That's it. All right, so here's basically another video of using the software.
On the computer screen, you are seeing my similarity search. If I take the mouse, and I don't know if you can even see the arrow or not, I think that you can, but here toward the bottom, they're going to give me a list of all of the possibilities that this compound could be. So I'm going to zoom in, just bear with me because I might have to focus once I get there, but If you take a look at the very top line, you're seeing that ethanol is ranked as number 1. So, eureka! I've just made some moonshine in the lab. So, ethanol confirms to me that I did produce the right reagent that I should have ended up with.
And I said reagent in that video, but it's actually a product because this was the end result, not the beginning result. So shame on me. All right, so here in the last slide, this is just an image showing you that I do clean off the ATR plate, and I do clean it off with either methanol or acetone. Methanol in a lab is going to be abbreviated MEOH for short, and this is what we use all the time. So I just give it a few douses of methanol, a few douses of acetone. I just wipe it off really well with a Chem wipe, not a paper towel, nothing rough. So a Chem wipe, a little bit softer, a little bit smoother, a little bit less damaging, but folks, it's a diamond. Nothing's really going to hurt it that much. And then I just put the whole thing back into the box, and I just put it back into the cabinet from which it came. All right, so I think that will kind of finish us up here. So we've just distilled moonshine. Normally this process, at least for me, took over 5 days, and for you, you've had to listen for an hour and a half, and you were able to see observations, and you were able to take measurements and record masses and record boiling points and, you know, FTIR data and everything else in between. You're also going to see the FTIR report uploaded in Blackboard as well. This is something that you do want to print off, and it's something that you want to attach inside of your notebook because it is a report that goes along with this data. So anytime this happens, you do want to print it, you do want to fold it, you want to tape it or staple it into your lab notebook so that way you've got proof that you did run an FTIR and that you had confirmation that it was ethanol in the very end. All right, so that's it of the fractionation and fermentation of ethanol or making moonshine. It's probably one of the labs that people like the most just because they can relate to it, especially if they're over the age of 21. And in addition to that, it doesn't really take a lot of work. I mean, you mix some things together in the beginning, you let it ferment for at least 5 days or longer, then you just distill it over and clean it up, and that's all that you got to do with it. So it is one of the favorites, I would say, of the summer class. And here we just did it virtually, and we did it together, and then you were able to see the observations just like you would if you were in class, and you were able to make some measurements just like you would if you were in class. You just didn't physically do it yourself. All right, so there's the fermentation of ethanol. Again, if you've got questions about the lab, feel free to reach out. You know how to get a hold of me. Take a look at your grade sheet. It will tell you exactly what to write in and what to do. You know, in the meantime, good luck writing up your lab notebook. I don't think that you need luck writing up the lab notebook, but at least good luck for good time's sake.